Okay, everyone, it's 4 p.m. in France. Welcome, everyone, to our first webinar talking about the 3D project, which is a CCUS project in Dunkirk, funded by an H2020 program and the European Commission. Thank you for coming today. There are a lot of people today. And so we are here to talk about an innovative technology, CCUS, and this specific project because in order to reach carbon neutrality, we have to reduce our emissions, we have to store some carbon. And one of the possible solutions maybe to generalize some storage of CO2 from very intense emitters like the sites of ArcelorMittal in Dunkirk. We've been working for now 3 or 4 years for this project, 3D, so it's 3D for DMX Demonstration in Dunkirk. And we've been working on an experiment on the ArcelorMittal site in Dunkirk, and we now have enough to share to you because CCUS in general and this project in particular raise so many questions about energy, about environment, about social issues. And so we've wanted to have these discussions with you and to answer some of your questions, guys, about all the questions you may have. Today, we're going to talk about the assessment of the project. We've been carrying out a life cycle analysis on the project to see if the project, of course, is efficient in terms of pollution and, of course, in terms of energy efficiency, because a CCUS project without energy efficiency would be useless because you don't want to spend too much CO2 to store the CO2 from the site. So I'm here with Vanya and David, and they're going to talk to you about this project, a general presentation of the project, and some key findings about the life cycle analysis. So I wish to you all great presentations, and do not hesitate to ask your question on the chat. I'll have a look myself. Thank you.
Just before starting, just to give you more information, if you have any questions during the session, please feel free to ask them in the tab at the bottom of your screen. You can also use the chat room to talk to each other. But at the end of the presentation, I will allow everyone to use their microphone. So if you want to share your question directly, you would be allowed to do so. If not, you can just write it and we will read the questions to Vanya and David so they can answer to you. So now, Vanya and David, I give you the floor.
Okay, thank you very much. I think it's up to me to start this presentation about the DMX demonstration in Dunkirk, the 3D project. So I would like to say thank you to everyone being here today, showing your interest by the 3D project and the decarbonation. So my name is Vania Santos Moreau, and I'm the project leader and the 3D H2020 project coordinator at IFP Énergie Nouvelle in France. And this 3D project has the support, as Thibault said, of the European Commission. And also we have a support from the ADEME, which is a French support. It's French support to this project, and I'm always excited to explain a little bit more about the 3D project. So the 3D project is a project that was developed for more than 10 years. David, you can past presentation, for more than 10 years. So the story of the DMX starts at IFP in Lyon and in Rail, which is near Paris. And the first things happened at more than 10 years ago. And some with the solvent screening, with some process modeling, and when with simulations of the process we developed, and we choose our solvent, we work it at the lab scale, and after we test the DMX process at pilot scale, because in Lyon, at IFP Énergie Nouvelle, we have a pilot plant which is capable to capture 0.2 kilograms of CO2 per hour. If I put myself near the unit, it's around 4 meters unit. And after the next phase and the last phase of the development of the DMX, it is the industrial demonstration in Dunkirk. And for this, in the 3D project, we construct a demonstrator, and this demonstrator is constructed now, and we are finishing the startup of the unit. But for now, we are already capturing CO2 in Dunkirk. So, David, can you? Okay, thank you very much. So the 3D project, as I said, is H2020 project, and there is three main objectives of this project. The first one is to demonstrate the DMX process for the CO2 capture. So as I said, we construct a unit, a pilot unit, and we call it a demonstrator because it's the last phase before the commercialization of the process. And here in the demonstration, what we want is to show that the technology it's capable of capture CO2. We will see if there is a degradation of the solvent. We'll see emissions, and it's really the last phase before industrialization. And so we connect our unit in the ArcelorMittal steel plant in Dunkirk. This is the first goal of the project. The second goal of the project is to prepare the first CCS large-scale demonstrator. Because, as you know, Dunkirk is near the North Sea, it's obvious. And as Dunkirk is near the North Sea, there is different possibilities to store the CO2. Of course, the CO2 can be used for products, chemicals, or whatever. But we can also store a part of the CO2 that will be captured in the North Sea. And for this, indeed, the 3D project, we analyze different sites of storage. One is near the UK. The second one is which we call the Dutch case, which is near it's Dutch case, so it's in interaction with Portos, Atos, and projects. And there is another case which is for us the most developed case, which is the storage near the Norway in interaction with the Northern Lights project. So this the different possibilities of storage of CO2, and we start with a case of storage 1 million tons of CO2, will be and are being is studied by the different partners of the project. That means that for each case, how we will transport the CO2, how it will be stored by pipeline, by ship. So this is studies that we are doing in order to see what is the most economical way to store the CO2. And the third objective of the project is see Dunkirk in the area of Dunkirk as a CCS hub. And we think that in 2035, Dunkirk, North Sea could be considered as a place to capture CO2 near Dunkirk in interaction of different industries in the area of Dunkirk, and the possibility to send the CO2 to the North Sea. And for this case, we are studying 10 million tons of CO2 per year. So the 3D project starts in 2019, and the initial duration of the project was 48 months. And last week we had the information that we will have probably more 18 months to finalize the project, because a project of this extension, we needed more time to finalize our project. So, David, if you can pass the slide. So the DMX technology. I'm not going to talk a lot about the DMX technology, because we'll have at the end of March a webinar that will be managed by our colleagues of Access about the DMX process, and they will explain how this technology is innovative. Today, I just want to show you some ideas about the DMX technology. As much of you probably know, it's a technology to capture CO2 based in the fact that we contact a flue gas with a solvent, and the solvent, which is it's a amine type solvent, have a high interaction with CO2, so there is an absorption of the CO2 in this solvent, and the solvent will transport the CO2 to in the first time in the amine-amine exchanger, and after in a decanter. I will talk about this later. And this solvent with the CO2 absorbed will be introduced in the stripper, or we can call it a regenerator. And we will, with temperature and in presence of steam, the CO2 will be produced, and the amine, the lean solvent, will be sent to the absorber. So we have the liquid being working in the circular mode, and in the middle of the process we have this piece, which is a decanter. And one of the characteristics of the DMX is that in presence of CO2 and in certain conditions of temperature and pressure, we will create two phases, one which we call a lean phase and a rich phase, and we only send to the regenerator the rich phase. So there is a lot of benefits of this type of process. One of the benefits, it's a low steam energy consumption. The fact that we have a thermally stable solvent with this kind of process, in certain conditions, we can produce CO2 in pressure at in pressure up to 5 bar G, which is interesting when we want to store it, and we can reach and we can have a very pure CO2. So, and we expect to avoid 30% of the capture costs. So the 3D demonstrator in Dunkirk. So we started in 2019 with a blank page, and today we have on site a unit, I'm sorry, working in a continuous mode. And just to give you some information about our demonstrator, it's always interesting. We have our site is a site which is almost it's a site of 50 meters per 80 meters, and our module, we call it a module, has 26-meter height. We have 3 columns, 2 absorbers, and 1 regenerator. We have around 10 cubic meters of solvent circulating in the unit, and we are capable to capture zero 0.5 tons of CO2 per hour, and we can have a capture rate from 90 to 99%. And we have here some of the main conditions of this process. Which is important to say is that we have also compressor units in order to put the CO2, to put the gas in conditions to be absorbed in the absorber. So, David. Yes. So, in schedule, in terms of schedule, so we start the construction of this demonstrator in at the end of 2021. The commissioning starts in March 2022, and we start the startup in October. And and from October to now, we are very happy because we are capable to have a unit operated 20 hours, 24 hours per day, 7 days a week. Um, and we had the first results, and we were capable to capture the maximal capacity of the unit. We don't see solvent degradation since October 2022. We have no foaming, and we have a solvent demixing as expected. So now, at the end of this month, we will start to product and start our research programs. That means that during 8 months, we will do the barometric tests, and my colleagues from Axens in the next webinar will explain a little more what we are going to do. And we also will do long-term tests in order to see how the technology runs with fixed conditions. And we expect to hand our operation in April 2024. So, David, yes. So, in terms of partners of this project, we are 11 partners working together, and it's really, really interesting to have all these partners working together. So we have ArcelorMittal, Total Energy, Axens, who are commercializing this DMX technology, and they and we work together to construct and operate the demonstrator. We have also the sequence group who product one of the molecules of the solvent. Also, we did studies in order to have to product steam on site, and this is a work from John Cockerill, Greenflex, and ArcelorMittal. Also, and after, we did studies about the liquefaction and the compression, and these studies were done by DTU, Air Products, and ArcelorMittal. And after, for the transport, we did 2 types of studies. We consider the ship transport and the pipeline transport, and this was studies of Breivik Gasco with Total Energy. And also in this project, we have a very important part is the analysis of the life cycle analysis, which will be presented by David Shu from the University of Zurich, and also we IFP and TotalEnergies work on the economical analysis of the process of the DMX process, and also we are doing some work with people from Dunkirk in order to make the project accepted by people around Dunkirk. So this is a 3D project. I think I did not forget a partner. I hope, and I really would like to thank you all for being here for this first webinar. We will start with the life cycle analysis, and just to say to you that in the 28th March, we will have our colleague from Axens, Louise Benoit, will explain a little bit more about the DMX process, the first results of the demonstrator. And in the next months, we will have a session about conditioning, and we'll have Nicolas von Sam from the TU, and we will have also a webinar about the transport and storage by Martin William Hay from Breivik and Svein Sloven from Gasco, and at the end of the year, IFP Énergie Nouvelle will came again to present the first results, the results of the demonstrators. So I hope you will enjoy this moment, and I let David continue this webinar.
Okay, thank you very much, Vanya. Good afternoon, first of all, to everyone. My name is David Schuh, and I am a PhD student at ETH Zurich in Switzerland. And I've been working on the environmental lifecycle assessment within the 3D project, together with colleagues from IFPEN, and of course with all of our experts within the 3D project who have provided the expertise and data for this analysis. Today I'm going to show you the results for the lifecycle assessment of a CCS supply chain that we have investigated within the 3D project. Before I start with the results of the lifecycle assessment, let me first of all, once again, show you why we are doing all of this at all. We have this demonstrator, and I'm showing this picture again because within the project we are very proud of it. And we are happy that we are able to demonstrate the DMX process at an industrial scale and under real conditions. And the purpose of this whole project is to really show that the DMX process works and where potential challenges may lie, and to advance the technology towards commercialization. So this process eventually should be applied in a large scale across various industries. However, we have to keep in mind the objective of this whole process is to reduce environmental impacts. We want to avoid the emission of greenhouse gases, and therefore we really need to ensure that we understand really well what the environmental impacts of this process are in the first place. Therefore, within the 3D project, we have prepared a lifecycle assessment for a large-scale CCS supply chain for a million-ton scale implementation of this DMX process at the Dunkirk steel plant. So how does this large-scale implementation of the DMX process work at the steel plant? Let us first have a look at the steel plant in its original state. So this is very simplified, of course. We have a steel plant, and in a traditional steel plant, we have primary steel production via the blast furnace route. And in the course of producing some steel, we will produce also a lot of blast furnace gas. Blast furnace gas mainly consists of nitrogen, carbon monoxide, but also large amounts of carbon dioxide. Yeah, so we are talking about roughly 1/3 of the weight of the blast furnace gas is carbon dioxide. And in the original system, the blast furnace gas is sent to a power plant, or in particular, it's a gas power plant, to be burned. In this way, the combustible elements of the blast furnace gas, such as carbon monoxide, can be removed. And then the flue gas is emitted to the environment. And this is also how the CO2 is released to the environment. As a co-product, we also produce some power as an output of the power plant. So the blast furnace gas is really a huge stream of greenhouse gases to the environment. So we are talking about a stream in the megaton scale. And because the concentration is so high, the blast furnace gas is really well suited for carbon capture. So we can capture the CO2 by adding a CCS supply chain to the steel plant. And I'm going to show you how this looks as an end-of-pipe CCS application. Instead of burning the blast furnace gas directly, the blast furnace gas is instead redirected to the DMX process, and the CO2 can be separated from the blast furnace gas. The blast furnace gas, which now has very low concentrations of CO2, is still sent back to the power plant station in order to remove the combustible parts, so we still have to do that. But because we have removed most of the CO2 already in the carbon capture process, the emissions to the environment are significantly reduced. Here, however, the journey of the CO2 does not end. We still have to take care of the CO2 that we have separated, and therefore the CO2 is first sent to a conditioning unit where we have to remove trace gases and where we have to condition the CO2 for further transport. And as Vanya already said earlier, Dunkirk is conveniently located right at the sea, and therefore we can use relatively low carbon transport options such as shipping and offshore pipeline transport. And depending on the transport mode that we select, the conditioning unit has to bring the CO2 in either a liquefied state or in a pressurized state. And then finally, the CO2 can be transported to some geological storage location. I would like to point out at this point that the DMX process itself, but also the conditioning process, are extremely energy intensive. We require both a lot of heat and also a lot of electricity. And we know that energy consumption is often associated with greenhouse gas emissions, which is problematic, of course. And therefore, the 3D team tries to reduce the environmental impacts, but also the cost of the CCS process by smart process integration. So instead of looking at the CCS process in isolation, the team is looking at the CCS process in combination with the steel plant. And at the steel plant, actually, there's a lot of unused waste heat potential that can be lifted in order to power the CCS process. And this way, we can, of course, reduce the amount of heat that we need to generate for the DMX process. And in addition, the team has also considered the use of locally available fuels. So I've already talked about the blast furnace gas, which can be combusted for power generation. The blast furnace gas could also be combusted for heat generation. Yeah, and this way we can use locally available fuels to regenerate the DMX solvent. Of course, in the environmental assessment, we have to then take into account all the consequences of doing such process integration. For the combustion of blast furnace gas, there would, for example, be the loss of electricity generation because the combusted blast furnace gas is no longer available for power generation. Okay, so now we have this very complex CCS supply chain added to the already very complex steel production process. And we know already from intuition that every single step of the CCS supply chain will result in some greenhouse gas emissions because we are consuming energy, materials, construction materials, and so on. So I think it's quite intuitive to now ask, first of all, does this whole CCS supply chain actually make sense? If we are emitting so many greenhouse gases, do we actually, in the end, achieve our goal of reducing overall greenhouse gas emissions? And then the second question that I, as a life cycle assessment expert, ask is, what are additional environmental impacts beyond climate change that may be caused by this CCS supply chain? And those questions we can answer using life cycle assessment. And I'm just going to give you a very brief overview about what life cycle assessment is. So life cycle assessment is a very nice environmental assessment method. What I like about it the most is that it considers multiple environmental impact categories. So we care a lot about climate change, of course, but there's also a lot of other environmental impact categories that we also take into account, such as ozone depletion, ecotoxicity, or water depletion. Furthermore, in life cycle assessment, we do not only care about local emissions and local environmental impacts, but we also care about the full life cycle. So for example, we care about where the raw materials come from that we use in our process and where all the materials go in the end. So about the waste treatment and recycling and the environmental impacts that are associated with those processes. And this is called a cradle-to-grave analysis. Within, so the life cycle assessment methodology is also standardized in ISO norms, so it's quite an established methodology. This was maybe now a little bit theoretical, so I'm also going to tell you how we conducted the life cycle assessment within the 3D project. So first of all, we benefit from experts from a lot of different fields that are working together within the 3D project to design a CCS supply chain in the megaton scale. And then from those experts, we were able to collect detailed inventory data for each and every single step of the CCS supply chain. For example, concerning the construction of equipment, utility demands, solvent production and consumption, and the lifetime of all the equipment. The only exception that I would like to point out is the geological storage, where we do not have an expert on our team, but where we have access to publish data by the Northern Lights project. This data that we have collected from our industry partners is what I call the foreground system. And this foreground system is then supplemented by background data from life cycle assessment databases in order to estimate the emissions that are caused in the life cycle of all materials, energy, and processes that are used in our supply chain. So for example, from the raw material extraction and from the end of life. And by combining those two data sources, we can estimate the emissions that are caused by the CCS supply chain and that are released to the environment. And then finally, we can evaluate those emissions using the environmental footprint methodology, which is the recommended methodology by the European Commission in order to evaluate the environmental impacts of the CCS supply chain. Okay, that was a very fast overview over how life cycle assessment works. Let's go back to our research questions. So first of all, let's have a look at whether the CCS supply chain actually reduces greenhouse gas emissions. And in order to answer this question, I am going to show you something that I call the life cycle carbon capture and storage efficiency for the CCS supply chain. And this is very easy to calculate and essentially a measure for the net avoided greenhouse gas emissions over the full life cycle of the CCS supply chain. So what I'm going to do is I'm going to take the amount of CO2 that I store geologically permanently, and then I subtract the life cycle emissions of the CCS supply chain, and therefore arrive at the net greenhouse gas emissions that I avoid over the full life cycle. And then finally, I divide this value by the amount of CO2 that we have stored geologically. And if I have 0 life cycle greenhouse gas emissions, I achieve an efficiency of 100%. But if I emit a lot of greenhouse gases along the CCS supply chain, I will achieve a lower efficiency and can even achieve a negative efficiency if I emit more greenhouse gases than I end up storing. Okay, and we know that this efficiency is highly sensitive to the energy supply, and therefore I'm showing you the efficiency as a function of the electricity supply, the carbon intensity of the electricity supply, and the carbon intensity of heat supply. So for the electricity supply, I can show you some values for rather low carbon electricity supplies, and on the right-hand side you can see carbon intensive electricity supplies. And the same I can also do for heat supply, where we have low carbon intensity heat from waste, for example, or higher carbon intensity heat when we are burning coal to generate heat. Okay, so for a very extreme case, I can consider electricity that is generated using hard coal and heat that is generated using coal coke, and then I arrive at this life cycle carbon capture and storage efficiency for the CCS supply chain that we have investigated. And this should be no surprise. The efficiency is very low. And why is that? Well, when we start from 100% of CO2 that is captured, we emit additional greenhouse gases in every single step of the CCS supply chain, in particular the energy intensive ones like the heat supply, the DMX process itself, or the conditioning unit. And this way, the life cycle carbon capture and storage efficiency is reduced to a very low value, in this case, 38%. I think this should not be a surprise when we are using fossil energy. However, I would also like to point out that even in this very extreme worst case situation, would still achieve a positive life cycle carbon capture and storage efficiency. However, I would also like to underline that we should still never get anywhere near this point, because a higher efficiency is still much better for the environment. Where are we actually in the 3D project? Well, in the 3D project, we really benefit from the location in northern France and the availability of waste heat from the steel plant. And this is why we end up all the way on the other side of this plot. So with a low carbon electricity supply from France and a lot of waste heat availability. And here we can see, if we again look at the contributions of the different steps of the supply chain, that we are almost able to fully eliminate the greenhouse gas emissions from the energy supply, just because the carbon intensity is so low at the ArcelorMittal plant in Dunkirk. Okay, and now we also see that actually, if we have achieved a very low energy supply already, natural gas, the transport step actually becomes the highest emitter. And this is because in this scenario, we have considered natural gas powered ships for the transport of CO2 to northern lights. Okay, so what do I learn from this analysis? Well, first of all, I've seen that the DMX process can already reduce greenhouse gas emissions today. And that is true even for the worst case of fossil energy supply. Of course, we do not want to use fossil energy supply for a CCS process, which will reduce our efficiency significantly. We aim for a low carbon energy supply, which is actually available in Dunkirk, and therefore enables us to achieve a capture efficiency above 90%. For the low carbon energy supply at the capture site, we learned that CO2 transport actually becomes the highest emitter. So next, I would like to have a closer look at transport options. And Vanya in her introduction has already mentioned that we are considering multiple storage sites for the 3D project. And in the base case, we are considering northern lights. So storage over 1,000 kilometers distance from Dunkirk. As alternative options, we have also considered a UK storage site and a Dutch storage site, which are much closer to the Dunkirk steel plant. In the results that I've shown to you previously, we have considered northern lights, which is quite far away. So now I'm going to consider a closer storage site, the Dutch one, which is only 200 kilometers distance from Dunkirk. Here you can once again see the results from the previous slides. And if I consider the Dutch storage site and shipping, you can see that the carbon capture and storage efficiency increases. And if I furthermore go on and consider pipeline, the efficiency increases even a little bit more. There's two things that I learned from this analysis. First of all, CO2 transport in the 3D project is already really low and benefits from the direct access to the sea. And the emissions from transport can still be improved by reducing transport distances, 1, and by switching to pipeline transport, 2. However, those improvements are rather minor compared to the improvements that we achieve by having a lower carbon footprint in our energy supply. Okay, going back to our research questions, I would, for the first question that we asked, does the CCS supply chain actually reduce greenhouse gas emissions? I can definitely say yes. And this is particularly true if we have low carbon energy supply. Next, let us have a look at the environmental impacts beyond climate change. And before I continue with the results on additional environmental impact categories, I would like to point out that we are considering a 1 megaton scale CCS supply chain, which is a substantial amount of CO2 that we capture from the steel production site. However, compared to the huge steel plant operation of ArcelorMittal in Dunkirk, we are still only addressing a fraction of the overall CO2 emissions at the steel plant. So we have to keep this in mind. So the megaton scale CCS supply chain implementation is not enough for full decarbonization of the steel plant. So it's only one step towards decarbonization, and additional measures will be necessary. For example, the CCS supply chain could be further scaled up to capture even more CO2. However, if we wanted to do that, we have to keep in mind that waste heat availability is limited. Yeah. So the waste heat potential that we have investigated within the 3D project is already used up for the 1 megaton scale CCS supply chain. So if you want to scale this further up, we can expect higher costs and probably also a higher environmental footprint. That said, let us continue with the lifecycle assessment results. And what I'm going to show you essentially is how much worse does a steel production process get if I add a CCS process on top of it. So I'm going to compare the environmental impacts of the CCS supply chain in the 3D project. I'm going to compare that to a generic steel production process that I've taken from literature. So in particular, I've taken it from the eConvent database, which is a lifecycle assessment database, and I've selected a European primary steel production process. What I'm going to show you now is a little bit complex. In this graph, you see a lot of different impact categories on the x-axis. Don't worry, you don't have to know all of them. I'm going to lead you through this plot later. On the y-axis, you see the relative change of the environmental impacts relative to primary steel production. So values that go up mean that the environmental impacts increase. Values that go down mean that the environmental impacts decrease. And in general, we can categorize those environmental impacts into two categories. Some which are more human health related and some which are more natural environment and resource related. Let us now first have a look at climate change. This is the impact category that we have discussed extensively earlier. We can see that for all of the steps of the CCS supply chain, we increase the climate change impact due to the CCS supply chain. However, this increase is overcompensated by the reduction that we achieve through storing CO2. And overall, by implementing the 1 megaton CCS supply chain, we can reduce the CO2 emissions, the climate change impact of steel production by about 6%. This is what we are able to achieve by implementing a megaton scale CCS supply chain. So what does this reduction cost us in terms of other environmental impact categories? Let's have a look at all the other impact categories. We see here now that all of the other impact categories increase. However, I would like to point out that mostly the impact increases are low. They are mostly below 1%, with two exceptions, which are ozone depletion here and resource depletion fuels here. And I think this is quite intuitive because the CCS supply chain is quite energy intensive. And therefore, if we want to run the CCS supply chain, we require additional fuels, in particular for electricity supply. This is also the reason why we have ozone depletion, because of the high electricity demand, which is satisfied by the French electricity grid, which happens to also have some ozone depletion impact. However, I would also like to point out that those increases are still relatively small and could be addressed by switching to alternative sources of electricity, such as PV or wind. The only outlier that I also want to point out is seen here on the right, which is the impact category ionizing radiation. And I would like to underline that this is probably not a representative result, because we are comparing the electricity consumption of the CCS supply chain from the, which is satisfied from the French grid, with which is dominated by nuclear power, and we are comparing the electricity consumption to a primary steel production in Europe, where we have much less nuclear power in general. So I would, so I say that this is likely strongly overestimated, and I would like to neglect this result, but I'm just still showing it for the sake of completeness. What I learned from this analysis is that the environmental impacts on the megaton scale CCS supply chain are relatively small compared to the steel production process. There are some impact categories where we see some increases, but which can be addressed by switching to renewable electricity generation. Just to summarize now the results, first we have looked at the greenhouse gas emissions of the CCS supply chain, and we have seen that the greenhouse gas emissions, that the DMX process can reduce greenhouse gas emissions already today, but low carbon energy is really key for achieving a high life cycle carbon capture and storage efficiency. And once we have achieved a low carbon energy supply, CO2 transport actually becomes interesting and the highest emitter in the CCS supply chain. We have further looked at the environmental impacts beyond climate change, and we see that they are mostly small compared to the steel production process. But for all of these analysis that I've shown to you, we have to keep in mind that we are only considering an implementation of a 1 megaton CCS supply chain, which is able to capture a fraction of the overall greenhouse gas emissions of the steel plant. And for full decarbonization, additional measures are required. With that, I conclude my talk, and I thank you all for joining this webinar. If you are interested in learning more about the 3D project, please feel free to join the other webinars that are going to be in a couple of weeks and still going to be announced. And with that, Ludivine, maybe you can continue with questions.